Okay, so this video is going to walk you through the basics of bonding that we've talked about so far in class, and so I'm going to start by just taking a look at the shapes in terms of hybridization. Now, if we talk about shapes as far as actual drawings go, you want to keep in mind that there's three basic forms of Lewis dot that we're going to look at, all of which are different energy levels. So the most simplistic form of Lewis dot we've been calling simple Lewis, and that would be where you're just connecting one single dot to another, where of course the dots are representing the electrons within the structure. When that becomes unavailable, some molecules can do coordinate covalent complexing, which is basically taking a lone pair of electrons and using them as a bond to an empty spot or an empty site. Our final step in Lewis dot diagrams, which we'll look at toward the end, is what's called expanded octet. In an expanded octet, you're asking yourself, is it okay for the molecule to actually access the d level electrons? In other words, is it in the third energy level or lower? Does it actually have d orbitals or not? And if that's the case, you're using a pair of electrons and you're literally separating them into singles. Now, if we sum this entire thing up, that is essentially all we're talking about with Lewis dot diagrams, is that it's one of these three things that are happening. For our purposes, most of the time we're working just in the simple Lewis and every once in a while a little CCC. Now for shapes, what we talked about was this idea of hybridization and kind of how these different things come to be. There are five basic shapes that we'll look at. When you have a centralized atom, in this case the yellow one, and there's two different attachments, you have to keep in mind that these attachments are the same basic structure. They're electrons. So electrons will repel one another since they are like charges, and you'll end up, if you just have two attachments or two sets of electrons, a linear shape with 180 degrees of a bond angle. You could imagine, of course, a third attachment coming in, and when a third attachment comes in, you have to visualize basically it coming in from one of the angles adjacent to the actual linear pair, and then sort of stretching or manipulating this shape to form a trigonal planar shape, which of course is still flat, but now has bond angles of only 120 degrees. And I'll show you examples of this as well. If a fourth one comes into play, here's where you start going into three dimensions. Because if you look from the side, this is actually has the most space in either the top or bottom of whatever you're calling your molecule. So if the fourth one comes into play here, you can imagine these adjacent ones shifting the opposite direction away from that and forming our three-dimensional tetrahedral shape, where it's literally shifting those bottom portions down and giving us now a substance that needs to be drawn in three dimensions, where we usually draw an up and a left, flat on the page, one coming at us and one going away. To go with fifth attachments, you could visualize any one of these flat spaces as having sort of the next availability for spacing. So I'm just going to pick this one. Here's where our fifth one would come in. And you can imagine it shifting these three flats away from this other one on the opposite side and forming almost a flat triangle in a centralized plane, which is what we end up getting with our fifth attachment, or our sp3d hybrid. You have a flat triangle in the plane and then almost this linear manipulation coming straight through the center. This is the hardest one for kids to visualize because it's a very complicated structure. We have an upward form flat on the page, a downward, one left, and then you have one coming at you and one going away. And I will use this as we start talking about how to draw these things out. If you're taking a sixth one, what's unique about the sp3d structure is that it has 120 degree bond angles on the plane or centralized plane here. So that's actually where you would access your next attachment, which would then shift everything on the plane away from one another into almost this square arrangement on the plane as the fifth one goes in. So with an sp3d2 hybridization, or 6 attachments, you end up with a structure that looks very, very similar to the tetrahedral, only it's got more faces. It's got 8 equilateral faces, 4 on top and 4 on bottom, giving it its name, it's octahedral. Now, what's important about all this is as we're constantly visualizing hybridization, all we're really looking at is this idea that there are only 5 varieties for molecules. You can have simplistic hybridizations that are non-expanded with our sp, our sp2, and our sp3, or you can expand the octet for molecules that go beyond the third level with a centralized atom and having our sp3d and our sp3d2. This will become really helpful as you sort of draw things out. So now the sheet I'm going to work through is actually a sheet practice on polarity. Most of these things on here just involve simple Lewis. So when I'm starting with this first one on here, I'm taking a look, and I'm just going to take the camera for a second here so you can see it a little bit better as I draw this. And I have CH3COOH. So when I draw this out, I'm taking a look and I'm trying to basically say, all right, what's going to be my centralized atom in CH3OH? I've got a carbon base sitting right here. I've got 3 hydrogen attachments, an oxygen, and then another hydrogen. Now, whenever you're drawing a Lewis dot, you need to make sure you draw in all your electrons as you go. Hydrogen, of course, has just a 1 valence electron, carbon has 4, oxygen has 6. And I'm pulling that basically just from the periodic table. Now, when you look at this, structurally speaking, you can see, all right, I'm going to connect a single to a single, a single to a single, single to a single, and a single to a single. So you end up with a structure that makes sense. Like, it's just this idea of connecting dot to dot. It's just simple Lewis. But we have to look at each center as having its own basic hybridization. So the first one on there, that carbon, has a hybridization of 4 different attachments. Your 4 different attachment, of course, would give you an sp3 hybrid. So carbon should actually be drawn as a tetrahedral. Oxygen is also an sp3 hybrid, but the big difference in oxygen is that 2 of those attachments are lone pairs. So when we draw out the finalized structure, we end up with a molecule that has a tetrahedral arrangement connected to a bent structure. And when I ask you the question, is it polar or not, you have to look and see, is there a molecule that's actually pulling very hard? And in this case, we have an oxygen pulling extremely hard, and it's going to pull electrons from hydrogen and from carbon and build up a negative charge on the oxygen and consequential positive charges on the carbon and hydrogen. So this molecule itself would indeed be polar. Now I'm going to skip around a little bit so that as we go through this sheet, we can kind of focus on some other ones besides just the simple Lewis. For example, if I'm trying to draw out xenon difluoride, which is the one right below it, xenon difluoride is much more challenging to draw, so you'll want to start with your pieces. You have xenon and 2 fluorines. Xenon has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Fluorine has a total of 7. So when you initially look at this, you'll say, well, how can a noble gas bond? And the answer is it can when it's connected to something that's very, very electronegative. So in this case, we can't simple Lewis anything to the central atom. We can't CCC. And so you ask yourself, can you expand the octet for xenon? Your answer is yes. It's just expanding because it has a D level electron. So it doesn't matter which pair you take, but you're going to separate the pair out and connect your singles. Well, now in order for us to figure out what this shape is, we need to count the number of actual attachments. 1, 2 bonds, 3, 4, 5, if you include the lone pairs. Well, 5 attachments is an sp3d hybrid. All sp3d hybrids are trigonal bipyramid. The big difference here is that 3 of these attachments are lone pairs. I'm going to pick my 3-dimensional sections and my spot to the side here as my actual locations for my lone pairs. The main reason being that's where there's more space. There's 120 degrees on a trigonal bipyramid versus the 90 degrees on the actual top section. So all 3 lone pairs are going to sit in that centralized plane, only you're not going to be able to see them. The only reason why we'll know they're there is because we end up with this shape that should not be. We have a shape that ends up skewing with all these lone pairs into a linear arrangement. And so although this molecule has extremely strong pulling from each fluorine, so we're pulling electrons very hard toward that fluorine at the top and this fluorine at the bottom, it's an overall non-polar molecule because the poles are canceling themselves out. It's essentially like you're saying you're taking electrons and pulling them up, but you're pulling them down just as hard. So the molecule doesn't end up going anywhere and the poles do cancel. So if we sum this entire idea up, what I'm basically saying through this entire structure is you want to keep in mind that as you're drawing Lewis dot diagrams, there's 3 basic components. But once you get it drawn, you want to think about hybridization. SP sp2, sp3, sp3d, and sp3d2. These are your only configurations you ever have to worry about. sp is your linear arrangement, sp2 is your trigonal planar, sp3 is your tetrahedral arrangement, sp3d is your trickiest one, your trigonal bipyramid, and sp3d2 is your arrangement where you have an octahedral. The only thing that ever changes is if some of these are lone pairs. And the only one you really have to worry about with lone pairs is your sp3d, because that one has 120-degree angles and 90-degree angles. So you'll want to actually place them on those 120-degree angles. There's tons of extra practice with this stuff. It goes through very fast as I'm talking about it. There's also additional videos that you can take a look at. But for the most part, these are the basics you'll have to be concerned with.